Alright, so thank you for joining me again, and in this video I'm going to continue this discussion of ionic and covalent compounds, or ionic and covalent bonding, and I just want to show you how we represent that on a sheet of paper. So in the last video we described ionic bonds as bonds that include a transfer of electrons, and covalent bonds are ones that give you share electrons. All right, sharing of the electrons are basically the glue that holds the atoms together. So I want to first talk about ionic bonding, and I'm going to keep it simple for you. But in order to do this, we have to go back and review some concepts of general chemistry that was called a Lewis dot structure, or a Lewis dot formula. So this is how this process worked. What happened is that to draw Lewis dot, if we had a compound like Na and Cl, two of these elements coming together to give us a compound, we want to represent this formation of a chemical bond on a sheet of paper. So how did we do it? Well, we started with Lewis dot structures, and Lewis dot structures are very simple to do. So let me show you how to do them. But first, we need to look at the periodic chart. So let me pull one up. All right, so we first need to find sodium and we need to find chloride. So if you look at the periodic chart, sodium, of course, is going to be over here to the left at atomic number 11. So I'm just going to kind of bolden that a little bit. And then chloride is over here to the right-hand side at number 17. Okay, so we have a left hand and a right hand side. So this is a metal and a non-metal. Therefore, we know it should be ionic bonding, and it is. If I did the electronegativity difference between the two, chlorine is 3, sodium is 0.9. That gives me a 2.1 as a difference. That difference is greater than 1.7. Therefore, it is ionic in characteristic. Okay, so how do we draw Lewis dot structures? Well, you first only need to represent the valence electrons. Okay, valence electrons, we said, were really the only most important things out of the subatomic particles that we need to focus on. So sodium has 1 valence electron. So that means in the Lewis dot structure, sodium gets 1 dot. Now, do you see how hard that was? Yeah, that's all there is to it to draw the Lewis dot structure of sodium. Well, we treat chlorine the same way. Chlorine's over here on the right-hand side. Up here at the top, we get number 7. So that means 7 valence electrons are with chlorine. So if I had to draw the Lewis dot structure of just chlorine, and that's it, I'm going to draw 7 dots. Go figure, right? Again, no one said that this was complicated. It shouldn't be complicated. So the way that we draw the 7 dots, remember we said electrons really don't like to pair up with each other. So we draw them separately first, and we go around like a clock. So I did one on top and one to the left and one down to the bottom and one to the right. And then they start to pair up when they run out of choices. So we start to pair them up from this point. So there's number 5, there's number 6, and there's number 7. Now, keep in mind that we also have the octet rule that's going to go into play, and octet basically means 8. Okay, so chlorine has 7, sodium has 1. We often say that it's very easy for sodium to lose 1 than it is to gain 7 more. So what I can do is I can circle this electron and I can kind of point it away, showing that sodium is going to lose that electron. And if I look on the chloride side, I see 7 dots around chlorine, and chlorine needs 1 more to get to 8. If he can get 1 more, then we can fulfill that octet for chlorine. So he's going to scavenge, and he's going to try to find that electron when he can. So that means that this electronegativity is very high. He's electron greedy. He wants it, because if he can just get that 1, just 1, then he's fulfilled the octet. So what I do is that I show that electron transfer basically getting completed, and I'll draw it over to the chloride side. And then what we end up with is what we call an ion stage. All right. And the reason that we call it the ion stage is because sodium has now lost an electron. So he becomes positive. That's how it gains that charge. And chlorine has now gained that electron, and that becomes negative because he's got one extra electron that's hanging out with him now. So this positive and this negative will come together, and that makes NaCl for my compound. And there's the balanced chemical formula for this. Keep in mind that this positive one is called the cation, and the negative one is called the anion. So all of these terms coming back, and I'm just kind of molding them all together at this point. So let's do another example, just so you can see that one more time. Let's say that we want to draw the ion stage, the balanced chemical formula, the electron transfer between magnesium and chloride. Okay, so I'm going to go back to the chart, and if I look at magnesium, magnesium is number 12. It's over here, right beside of sodium. So that means that he's got 2 valence electrons. So on this Lewis dot structure, I'm going to draw my first one, and I'll draw my second one. Now, chlorine, we said had 7. So 1, 2, 3, 4, 5, 6, and 7. There we go. So I want to show the electron transfer that happens between magnesium and chloride, and I do this basically the same way. I say, well, you know, it's easier for magnesium to lose 2 than it is to gain 6. It's easier for chlorine to gain 1 than it is to lose 7. So one of these electrons I'm going to circle, and I'm going to draw it here to that chlorine. Okay, but now we have a problem, because magnesium still has 1 that he's got to get rid of. He's got to find somebody to take this stuff, right? Who's going to take it? Well, what you have to keep in mind is that in a typical environment, there's tons of magnesium, not just 1. There's tons of chlorine, not just 1. So I can go through and I can draw another chlorine down here with 7 dots around them. There we go. And this allows magnesium to say, oh, hey, you extra chlorine out there. I've got this extra baggage and I'm trying to unload off of somebody. So would you like to take this handout? And that chlorine says, absolutely, I need that one. That will allow me to fulfill my octet, and I'm a very happy person now. So magnesium has to give 1 of the electrons to the first chlorine and the other electron to the second chlorine. So this is showing the ion, or the transfer, electron transfer step. Now we want to show the ion stage, or the ion step. So what we've done is that we've brought in magnesium with a positive 2 charge, and there is the cation. And then we've brought in chlorine. Well, notice each chlorine only gained 1, right? So that means each chlorine is only going to have a negative 1 with it, because that's all that they've done. Now, I know that we've drawn 2 of them, but as far as gaining or losing electrons, each of those chlorines, they're all chlorines, they all behave the same way, they've only gained 1 extra. So this is a negative 1 for me. However, we did write down 2. So I'm going to write down a big 2 out in front here to show you that it's going to take, for this transfer to happen, it's going to take 1 magnesium and it's going to take 2 chlorines in order to do that. Well, I can then finish that up with a balanced chemical formula. And that balanced chemical formula is Mg and Cl. These 2 things come together. However, there's 2 chlorines, so I want to put a small number 2 down there below. So there's MgCl2. Folks, that's the balanced chemical formula for magnesium chloride. Again, this is how the charges are assigned. If you looked at an ion chart, you're going to see positive 2 for magnesium. This is why. It's got 2 valence it's got to get rid of. It's got to get rid of those. It's got to transfer them over to somebody so that way it can be happy with its newly found, quote, octet. Okay? Chlorine, if you looked at an ion chart for chlorine, you would see a negative 1 up at the top, and that's the reason. It needs that 1 electron to fulfill the octet. So, if we get a relationship here, between Mg and Cl, it takes 2 of the chlorines to balance out that magnesium charge that it brings to the table. Hence, MgCl2 is the structure. Okay, so that's a little bit about electron transfer. So this is something that you might see on a test on the very first one. Again, look, all of my hints, I'm giving you hint, 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 hint. So you probably will be asked to draw the electron transfer between two atoms and then keep it going until you actually see something that matches up and that might work. You might have to add on a third one here depending on what it is, or you might have to add on another one over here. You might have to go through another magnesium or another sodium or whatever the case is in order to make this thing work. So for instance, Na and O. Well, sodium has 1 and oxygen has 6, right? 1, 2, 3, 4, 5, and 6. So electron transfer says I'll circle that one, I'll bring it over. This sodium's happy, but that oxygen is not. So I'll have to bring in another sodium, and that other sodium will carry with it another 1 valence, and I can circle that one and show that it also goes to that oxygen, and now oxygen has octet as well. So this is going to give me Na+, but there's 2 of them, and this gives me an oxygen that carries with it a -2, and that means that the formula that happens between these two things is Na2O. There's the structure or the formula for sodium oxide. Okay, again, this is where the charges are coming from. I know that you have ion charts that are out there that you can use, but where do those charges come from? This is where they come from, folks. It's all about electron transfer and what these atoms or elements typically want to do, and it's all driven with electronegativity, and it's all driven due to the octet rule. Bottom line, that's how these things work. Now, this is representing ionic compounds. And we've already said that in organic, we are going to focus on covalent compounds instead. So covalent compounds cannot be shown with electron transfer. Okay, electron transfer is just for ionics. That's it. So if we have something like CO2, I cannot draw the Lewis dot structures and represent them this way. It's not going to work for me. CO2 is covalent. Transfer does not happen. If transfer does not happen, then these arrows cannot be drawn on a sheet of paper. I should not represent it this way. I've got to represent it a different way. But we still use Lewis dots in order to do it. So I'm still going to look at Lewis dot structures, and I'm going to look at valence electrons that come into the picture. But we're just going to do it in a different way. We're not going to show the transfer of electrons because transfer does not happen. So we need to pay close attention to a Lewis dot structure now, an actual structure of a molecule. And there's a couple of rules here, but quite honestly, instead of going through the rules, I just like to start drawing examples down onto a sheet of paper so you can see what I'm doing. So let's draw the Lewis dot structure for HCl. Okay, how do we do this? Well, we do it very similar to before. I have hydrogen and I have chlorine, right? And if I go to the periodic chart, I'm going to see hydrogen up here to the left, and that is a 1. So there's 1 valence. And then I'll look to chlorine over on the right-hand side, and there's 7. So there's 7 valence that are there. So I'm going to write that down. 1 valence and 7 valence. I only have 1 of them apiece, and what I'm going to do is I'm going to add them up. So 7 plus 1 is 8. Well, most of the time we start with the center of a molecule, but there's no really center here because there's just 2 things, and that's it. But it's kind of like that game where you got to connect the line. So we've got to connect the line, and that goes kind of crooked. All right, so let me draw that a little bit straighter. There we go. H and Cl get connected. So, number 1, we do what we call a total valence electron count. And that is what we did up here. Okay, I broke them down into the individual elements. I looked at how many valence each one brought to the table. If I did have more than one, then I would do a multiplier, very similar to formula weight, and I would add them all up in the end. So this is the total valence electron count. Number two, you determine what the center atom is going to be. And hydrogen can never be the center of an atom. Okay, that's just one of those rules that we're just always going to follow. Well, in this case, we didn't really have a center. There's only two things, so we don't really have a full-blown center atom because we just have one to the left and one to the right. So it made our job a little bit easier because of that. All right, number three, we're then going to connect all of the atoms to the center if we can. Well, again, we didn't have the center, so we just connected the atoms together, and we did that with a line. And this is going to represent a bond, and a bond always represents two electrons, okay? So by drawing this line, this is two electrons right here. Well, I only have 8 that I can actually assign to this structure. I've already represented 2 of them. So I'll subtract 2, and this gives me a total of 6. I've got 6 left. I got to figure out where they go. Well, hydrogen, this is kind of a funny one because hydrogen really only wants 2 maximum. Remember, he's in that very first row of the periodic table, and it's just hydrogen and just helium. So hydrogen's one of those odd ones, again, that doesn't necessarily need 8. He's okay with 2. And as long as he fills at 2, then you move on about your business. Well, hydrogen in this case already has 2. It's got this line that's connected to it. That represents the 2 electrons right there. So we do not need anything else around hydrogen. Hydrogen's completely happy at this point, folks. So we have to represent 6 dots somewhere. Hopefully chlorine needs 6 of them. If so, then it makes our job a little bit easier. Well, if I look over here to the right-hand side, chlorine has this line, which represents 2. Chlorine wants 8 in total to fulfill the octet. And guess how many he needs? He needs 6 in order to get to the total of 8. So good news. 1, 2, 3, 4, 5, and 6. There we go. So if I double check the math, I have 2, 4, 6, and 2 from the line is 8. So that satisfies chlorine. If I look at hydrogen, there's only 2 there. That satisfies hydrogen every single time. It doesn't need any more than that. And then if I look at the total number that's represented in the structure, I can do the count one more time. 2, 4, 6, 2 from the bond is 8, and there's actually no more dots or no more lines anywhere else to count. So that gives me a total of 8, and sure enough, I have 8 as a total. So this is what we call the Lewis dot structure of HCl, which is hydrochloric acid, or hydrogen chloride if it was the salt. It could actually come to us in either form. But this is the Lewis dot structure of HCl. Okay, what else can I say about this before we stop this video and do more examples of this in the next one? Well, we can talk about something called polarity, all right? And polarity basically means an unequal sharing of electrons. If I look at this structure, these electrons are unequally shared. It looks like a lot of the electrons are over here on the right-hand side, and there's none on the left-hand side, right? This is an unequal sharing of electrons. So because of that, this structure is what we would say polar, because there's unequal sharing. So let me just redraw the dots back. So this molecule is polar, check. And sometimes they will say draw the direction of the polarity. So the way that we do that is we draw a line and we put an arrow onto the side that points toward the most negative side of the house. And on the other side of that arrow, we put a little dash mark. And that dash or that tick mark, well, if you kind of erase the rest of this arrow, you see what that tick mark represents. It means the most positive side of the house. So that tick represents the most positive side, and the arrow points toward the most negative side. So this is the direction of the polarity, and this is how we determine that. So water is polar. Therefore, HCl is polar, and therefore I can mix the two together, and they will mix, and they will be miscible. All right, that's good news, because this is how hydrochloric acid is made in a lab. I take HCl, I dunk it down into some water, I make a solution of it. It's about 37% HCl solid, and this gives me hydrochloric acid that's concentrated after that point. I mean, that's just why that works. The other term that they will use here, if they don't use polarity, they will use the word dipole. Dipole, di means two, pole means polarity, which means a positive and a negative. So if they don't use the word polarity, they could use the word dipole. Dipole basically means the same. It's an unequal sharing of electrons. If they say show the direction of the dipole, well, that basically means the same thing as what we just did. They want you to show the arrow, and they want you to point the arrow toward the most negative side, and then draw that kind of tick mark onto the most positive side of the house. So, dipole and polarity are basically words that are used interchangeably here. They both mean the same thing. So that's where this video is going to stop, and we're going to do many more examples of this Lewis dot structure in the next video. And the reason is because this is pretty important when it concerns organic chemistry. So it is something that I want to do more examples of over and over and over until you feel comfortable with these, because this is a pretty large part of what we're going to be doing all semester long, and you need to be comfortable with that. So see, I'm going to spend a little bit of extra time, and I'm going to make sure that you walk away as Lewis.pros.